Recording in progress.
Okay, appreciate the wait, guys. We're gonna get started. So some quick announcements I want to make. Raise your hand if you're interested in doing projects with us. Hopefully that's most of you. Okay, I like to see it, like to see it. So uh again, those will be posted in our Discord later this week, so please keep your eyes peeled. Um, the two clients that we will be going with this year is LMI and John Hopkins APL. And so we have a total of 6 projects combined with them. Oops. And so yeah, total of 6 projects between those two clients. Of course, we do work with UVA departments as well. So we have more than just those 6 clients. So yeah, so I'm just trying to reverse this camera. Yeah. Our projects are application based, but again, some of them, a lot of the UVA ones especially, we are looking for beginners. So don't be too worried if you don't get anything. Plus, you do take new clients on a rolling basis as well. So again, it's not the end of the world if you don't make it the cycle. Okay, so if you have any questions, by the way, about applications, please just post them in our Discord in the general questions channel, or just stay after lecture and I'll be happy to answer anything. Okay, so let's just do a quick review of last time. So last time we started with a kind of a breakdown of the difference between AI, machine learning, and deep learning, right? So to put it, AI is kind of the broadest bubble where any algorithm that just tries to be smart can be called an AI. It's a very loose definition. You can get away with calling really anything an AI. Machine learning, though, is when you take data and you improve your algorithm using said data. Like your model has some way of adapting, right? Deep learning is where we use something called neural networks to undergo that learning process, right? So that's why it's deep learning and machine learning. The deep refers to the neural networks, which we'll cover later today. Yeah. Okay. And so our overarching goal though with this deep learning idea is how can we have kind of a one size fits all algorithm where like for really any arbitrary trend in data, any arbitrary function in our data, we can just kind of throw a model at it and it'll like learn that pattern, right? We kind of want the same model to be able to learn like y equals mx plus b, quadratic formula, the cubic formula, right? It could also be like, beyond your normal math formulas, like, based off of what I ate today, what am I going to do tomorrow? Right? Like really any arbitrary function, can we make a single model that can learn any of those functions? And so what we ended on was the perceptron, which can't do that, but it is a building block for neural networks. So with a perceptron, it takes in a set of inputs, right? So in this case, the inputs are in green. And we control 2 types of parameters. Weights, right? So for each input feature or category of input, we assign a single weight value to it. So in this case, for any input under humidity, we assign that to a weight of 0.5, right? And so the weight controls how much each feature or category of input contributes to the outputs. Yeah. Now you could say, okay, what happens if the inputs are all zeros, right? 0 times anything is equal to 0, right? Does that mean the output should always be 0 as well? Not necessarily. So the bias is a second type of parameter that is independent of those input features, right? So again, with weights, we multiply each weight by the input features. We sum those together. That's where we got that 35.5. And then we add a bias term. So it's not impacted by any zeros in our input. And then finally, we pass it through something called an activation function. And for now, last time we kind of skimmed over that. We'll go a little bit more in depth here. Does anyone remember is this example supervised or unsupervised learning? Just raise your hand and go for it.
Supervised.
Supervised. Supervised learning has two kind of sub-problems, right? Regression and classification. Is this regression or classification? You just raise your hand and go for it. Regression. So again, supervised learning is when you know what the output should be, right? And so you use what that output should be to improve your original model. And regression is when what you're trying to output is a continuous value. In this case, rainfall, right? Classification is when you're outputting a set number of categories, right? Like output, am I happy or sad, right? 0 or 1. That's classification. Okay. So moving forward. So the interesting thing about this perceptron is that it's glorified of y equals mx plus b. Actually, when you only have a single input feature, so it's one feature, it literally is y equals mx plus b. It's just the equation of a line, right? So what this means is no matter how many input features we have, our perceptron can only ever learn linear relationships between the inputs and the outputs, right? So can someone try to define what is a linear relationship? A straight line, exactly. For example, if we change temperature, it'll always impact the output by minus 0.2, right? Independent of what the temperature is, right? Increase temperature by 1, it'll output will always decrease by minus 0.2, right? And obviously, you can see how that's kind of a problem. We can't even learn quadratic functions. We learn how to solve quadratic functions in algebra 1 and 2, right? So how can we make this a little bit smarter, right? Yeah, so this is just an example of writing out this graphical representation as kind of a function, right? So just a brief review of classification. We just have an extra step of having something called a sigmoid function. All that does, the sigmoid function, is that it takes an input, right, and maps it to a 0, 1, right? If the input is negative, it'll map it closer to 0. If it's, sorry, it maps it to a number between 0 and 1, right? The more negative the input, the closer it is to 0. The more positive the input, the closer it is to 1. Okay. Yeah, so this is kind of the example, right? Like with this quadratic data, all we can do is fit a line to it. And so we ended last lecture with how can we model nonlinear relationships and, right, how do we actually pick these weights and biases, right? Like last time, last time I was just like, so yeah, here's weight 1, weight 2, bias 1. I was just like playing around with the slider, right? You can imagine if I have hundreds of weights and biases, you can't just open up Desmos and well, you could, but it would take you a very, very long time, right? We want something much smarter than this. So, yeah. Oh, that was not shared at all. My bad. I meant to click that. Sorry. What I was just doing is, I have my weight 1, weight 2, and bias 1. Yeah, like all I can do is if I want to choose ideal weights and biases is well, pick them myself. You can imagine when we have a bunch of weights and biases, this is not feasible. Okay, so that's the end of review of last lecture. Does anyone have any questions before we keep moving? No? Okay, sounds good. As always, just feel free to interrupt me and just raise your hand if you get stuck on anything. Okay. So before we move on, let's kind of clean up our graphical representation, right? All I'm doing here is all this stuff in this gray box. Let's just kind of hide that or abstract that away into a gray circle, right? So this is the representation I'll be working with moving forward. So, we still have our 3 inputs, but they feed into this neuron or perceptron, and then we get the output out, right? So the multiplication of the weights, the addition of the bias, passing that through the activation function, all that's still happening. I'm just hiding it away. Does that kind of make sense? So what's going on here is we have a bunch of those perceptrons or now neurons that are still taking an input and still outputting stuff, but now they just feed into each other. Again, a neuron is a perceptron, it's just a perceptron that's in a neural network. So when you have a neuron by itself, it's a perceptron. When you have a perceptron that's part of a network, we call it a neuron. They're the same thing. Okay, great. Okay, so our neural network kind of has 3 types of layers, right? The input layer is just inputs, right? These are just, a row in your spreadsheet, for example. Hidden layers are kind of your intermediary stacks of neurons, right? So with your hidden layers, you have the outputs of your previous layer feeding forward into them. And then each neuron has an output that then feeds into the next hidden layer, right? Your output layer is also a neuron, but it controls the number of outputs you have, right? So what does that kind of mean? Well, in a regression task where you're outputting a single neuron, a single value, you only have one output neuron. In let's say you're trying to predict 10 different classes. We'll cover this later, but you would have 10 output neurons, right? Okay. Um, so again, the gray and blue, those are all neurons. The green, those are just like input numbers. Great. And again, in a neural network, data always flows forward. It doesn't flow backward, or for now, it doesn't really flow backward. And it doesn't go in between layers, right? So again, neurons in the same layer are independent of each other, right? At least when we were passing data forward. Okay. So I'm back to I was hiding away those weights and biases, but what's really going on is remember, each input for any given neuron is mapped to a weight, right? So now I'm just drawing out those weights. So here I have a very simple neural network with 3 neurons and 1 hidden layer. So again, the gray is our single hidden layer, and the blue is our output layer with just 1 neuron, right? So again, because we have 2 input features, right? Each of these neurons have 2 weights, right? They have 2 connections going into them. And again, they still have a bias, right? I just kind of wrote it down there. Okay. So again, if we just zoom into this top neuron, the one that's outlined in orange, we'll just see, hey, it's the normal perceptron stuff, right? We still have those 2 inputs, same as last time, right? And we feed those, each input is assigned to a weight, multiply them together, sum them to get 0.75, or sorry, sum them to get 0, add 0.75, and then we pass that to an activation function. So now in a neural network, before in a perceptron, we just we didn't really care about that activation function, right? In a neural network, the activation is very, very important. So in this case, the activation we're using is something called ReLU, right? All it's really doing is if it's a negative number, like if the input is negative, it outputs 0. Otherwise, it doesn't change the input. So for example, with an input of 0.75, it doesn't change the input. Now, if the input was negative 0.75, the output would be 0, right? It's taking the max between the input and 0. And so ReLU is a nonlinear function. If it was linear, it would just be a straight line, right? So kind of the conceptual idea of ReLU is you can imagine it as kind of like a switch, right? If your input is negative, that means you kind of turn that neuron off, right? If the input is negative, this entire neuron will always output 0, right? If the input is positive, then we kind of keep that signal going. So in our greater neural network, what ReLU is doing is for certain types of inputs, it's like turning off certain neurons. Does that kind of make sense? Like for example, with 2, right? But yeah, let's go through another. Yeah. So with 2, right? The input to this activation, I believe, should be positive, right? So both neurons are activated, right? Whereas if we had a different input, right? One neuron might be activated and the other one might be off, as in it outputs a 0. And so that way we can have a lot more complex functionality, right? So depending on what the input is, certain neurons are turned on and off. That's kind of the visualization. Yeah. Okay. Any questions about what I was kind of going with that? Yeah, go for it.
Could we have the first 3 neurons in this layer 1?
Yeah.
For the person.
You could. You 100% could. We usually don't. Because it makes a process called training or backpropagation a lot more difficult. And I'll get to that later in the lecture. But you could. You definitely could. Great question though. Okay. So again, let's take a look at our last layer, right? For our last layer, we're doing binary classification at this point. So we're treating our activation as just a way to like format our outputs, right? So before in our hidden layer, we're using ReLU to like have this idea of nonlinearity of turning off certain neurons. Now with our output layer, we're just trying to format our output into a probability, right? So for yeah, so you kind of see that the activation function kind of has two purposes depending on what type of layer it's used on. Okay. Yeah. So any questions about this? I kind of skipped through the weights and biases calculation. Do you guys want me to go over that or are we good to go?
You add the values outside of the neurons, so they go to the output layer.
Oh yeah, yeah, are you talking about like these biases and weights?
So there's biases for each neuron, and there's biases between layers as well.
Oh, sorry, no. Sorry if it's a little bit confusing. These weights that are being like drawn out, like that 0.5 and that minus 0.5, those are like, yeah, I'm just illustrating these blue guys. Yeah, that's for that neuron. Yeah, so he was asking like, are there weights outside of the neuron or like biases outside the neuron? No, like I'm just trying to visualize like these blue weights and like that purple bias, right? So 0.5 minus 0.5, 0.5 minus 0.5. Good question though.
Oh, so every neuron has an activation.
Exactly, yeah. Every neuron has an activation function. In this case, all the neurons in the same layer had the same activation function of ReLU. And the activation function of the output layer had the sigmoid. And again, that's just mapping an input to a number between 0 and 1. Right? Again, binary classification, we output a discrete number, right? So while our sigmoid function gives us 0.32, we round that to get 0, right? So in this case, we only have an output of 0 or 1, and our output is 0. Okay, any more questions before we keep moving? All right, perfect. Okay, so now with this idea of neural networks and these nonlinear activation functions, can we just with our simple 3 neuron network, can we now fit to this better than just like a simple line? The answer is yes. Yes, we can. So this is in the lecture if you guys want to play around with this. But I know there's kind of a lot here. But all I'm really doing is like I wrote the function for sigmoid. I wrote the function for ReLU, right? And this is just like the equation for a single neuron. So you see there's our weight, there's our second weight, there's the bias, X and Y are my inputs, right? So all I'm doing here is I'm just like writing my neural network as a function. That's all I'm doing here. This is like in Desmos, this is our neural network. So you can see if I play around with these weights and biases, I get some pretty fun ways that it modifies our separator. Again, this is visualizing our classification. This is a little bit of a review from last time. Does anyone remember why I'm graphing this inequality equal to 0.5?
Is the signal function crosses the y-axis at 0.5?
Yeah, so at 0.5, like if my entire neural network outputs 0.5 for binary classification, right? Again, a number mapped to less than 0.5 goes to a class of 0. Let's say like I'm predicting if I'm hungry or not, right? Not hungry is 0, hungry is 1, right? If I output 0.1, that means, well, round down to 0. If I output 0.9, round up to 1, right? What happens if I output 0.5 on the dot? Well, that means I'm literally unsure at that point, right? So you could then think that anything above 0.5, so anything above this line is mapped to one class, and everything below this line is mapped to another class. So that's kind of why I'm visualizing this equals 0.5 line. Does that make sense? Okay, great. Again, you guys can feel free to play around with this if you want. But yeah. So we're not quite learning the equation of a parabola by any means, but we are able to separate said data, right? Okay. So this is only possible though because of those activations, right? What happens if we take out the activation or like the activation is just like our identity function, the input equals to the output. What happens if we were to do that? Well, it turns out if we remove that activation, our entire neural network just boils down to a single perceptron, right? So again, this is like our neural network. So like, we have our inputs, X1 and X2. The output of each layer is, the output of this neuron is O1. The output of this neuron is O2, right? So, if we plug in the inputs of these output neurons into H3, which is our final output neuron, you can see that we can group the weights together, right? And it turns out that like this grouping of weights, right, is equivalent to like learning a single weight, if that makes sense, right? Like, in other words, instead of trying to learn these 4 weights, right, why couldn't you just learn like W3, W31, W11 plus W32 plus, times W21? Why don't you just assign that to a W, like a big W1? Does that kind of make sense? So if you take out the activation functions, this just boils down to like, hey, let's just try to learn this bigger weight matrix instead of trying to learn 4 separate weights. So it boils down to a perceptron at the end of the day, which, as you guys know, can't learn nonlinear functions. If you have any questions about this math derivation, by the way, please feel free to stick after. I'd love to break it down more. Okay. So we just covered ReLU and sigmoid. Again, sigmoid is converting things into probabilities. ReLU is just 0 or don't change the input. There are a ton of other, like a lot more than the ones I have listed here, right? And again, activations have 2 purposes. If it's in the hidden layer, it's to introduce this idea of nonlinearity. And that idea of nonlinearity lets us learn these really complex functions, right? If it's in the output layer, all we're doing is like transforming that output into a format that fits us. Again, in the case of classification, that's transforming the output into a probability. In the case of regression, what activation would we use? It's kind of a trick question, by the way. In the case of regression, what would be a reasonable activation for our final output neuron? You just raise your hand. Try to go for it. Well, remember, with regression, we're outputting like a single continuous number, right? So do we generally have restrictions on on a continuous output? No. So on your output for regression, on your output neuron, you can just like not really have an activation. And that's what you normally do. In regression, your output, the activation function on your output neuron, that's usually just nothing, the identity function. All right. Okay. Any questions about activations, by the way? All right, great. Okay. So kind of the idea is, and again, in our toy example, we each have 3 neurons, one input layer. But the more neurons we add, either by adding more and more layers or by making our layers wider, the more and more like complex functions we can kind of create, right? So this is our example with 3 neurons. With 5 neurons, we can have we can express way more complex functions. Like this guy has like 1, 2, 3, 4 corners, or 1, 2, 3, 3 corners. Sorry. This one only has 1 corner, so to say, right? So the more neurons you add, the more complex functions you can model. But so again, this goes back to the idea of bias and variance. With bias, you have a high bias term or a bias error when you have a very simplistic model that can't really model complex functions. For example, a perceptron, we should only model like a straight line. That is a very high bias because it can't model complex functions. Whereas neural networks with a ton of neurons, those have a very low bias because in theory, they can model any function you want. On the flip side of that, we have the idea of variance, where this kind of measures how complex a model is and thereby how sensitive it is to new data. So I'll go a little bit more into variance later, but for now, just remember that a perceptron has a very low variance and a neural network has a very high variance. It's very sensitive to new data. That'll be clear in a little bit. Okay, so before we move on to like how do we actually choose these weights and biases, again, for now, I've just been like picking them through Desmos. I just want to go over the task of multi-class classification. Again, we've done regression and classification. What happens if we want to output more than one class or we have more than one category? For example, let's say we want to output precipitation, right? Well, they could be snow, rain, or neither. So we have 3 classes in this case, right? So we still follow our same structure of, inputs feed into hidden layers of neurons, which feed into output layers. But we have a little bit more vocabulary. So in this case, the output for each output neuron is a confidence value between 0 and 1 for that category, right? And yeah, and so yeah, I'll go into logits in a little bit. But again, since we have 3 possible output categories, we have 3 output neurons, right? So again, the final output, I'll explain what this is in just a second. But the final output of each neuron is, again, a probability. So you could say with 86% confidence that, hey, it's going to snow, right? Whereas you say with 1.5% confidence that it's neither going to snow or rain. So we want these nice probabilities because it's very understandable, right? We have an 86% confidence of this thing, 1.5% confidence of this other thing, right? So so the direct output of our neurons, we call these logits. So these are just continuous numbers. So 3, 1, -1, it could be like 0.75, right? We want to map these numbers onto probabilities, right? So to do that, we have an activation function called a softmax function, right? And so it's very similar to just a percentage, right? Like the simple way of thinking about it is like we just add up all these numbers, or rather the absolute value of these numbers, and then just 3 divided by 5, right? 1 divided by 5, right? But instead of doing that directly, we raise that number, or we take e raised to that logits. So we do e raised to 3 divided by e raised to 3 plus e to the 1 plus e to the -1, right? So as you guys should know, like raising some number to a power will always output a positive value. So it's kind of like taking the absolute value. But yeah, so why would we ever do this e stuff though? Does anyone have any guesses? Like, why don't we just take the absolute values and sum them and, just do that? It's a bit of a tricky question though, so it's totally fine. But
Okay, the bigger numbers.
yeah, that's on the right track, right? So by doing e raised to 3 instead of just like absolute value of 3, we're exaggerating the differences between the outputs, right? So notice that like the difference between like 3 and 1, for example, is like 2, right? Whereas the difference between like 0.867 and 0.11, that's like a pretty big relative difference, right? So we do this raising to the e to exaggerate differences between the outputs. That's all we're doing. Does that make sense? In theory, you could do like some absolute value thing, but we like to do this e, one, because, well, it's a smooth function, but 2, it also exaggerates those outputs. And so in this case, we do something called the argmax. They're just taking the maximum outputs. So in this case, the maximum output was from a first class. So let's say this first class is mapped to 0, this one was mapped to 1, this is mapped to 2. Think of it as like indexes of an array if taking like Python 1, or sorry, Intro CS. And so we just take, our output is the argmax of this final layer. So in this case, the 0th term, the class 0, it's going to snow. Does anyone have any questions about kind of the softmax or like multi-class classification? All right, fantastic. Okay, so quick review. So neuron, what is a neuron versus perceptron? They're the same thing. They're literally the same thing. It's just we call it a neuron when it's in a neural network, right? So if we have an inputs, like n different, like so in this case, humidity, temperature, wind speed, we call those 3 things features, right? Each feature is mapped to a single weights, right? So again, if you're thinking of like columns in a spreadsheet, right? All of those humidity values will be multiplied by 0.5 in this case, right? Same with temperature and wind speed. We don't have a weight for each like input value. We have a weight for each column or feature. Okay, and then we pass, multiply inputs by weights. add a bias, and we pass it through an activation function, either to one, have this idea of nonlinearity to learn complex functions, or two, on our output layer, format our output into a probability, for example, or just keep it the same, right? If we're doing regression. Okay. Yeah, so again, we have two tasks in supervised learning, regression and classification. I think we've kind of belabored that point, but okay. Now here's kind of the big second topic. So we have this cool neural network, we have this structure. How do we actually pick these weights and biases without opening Desmos, right? Okay, so the idea of figuring out our weights and biases, this is called training, right? So here I have like the rough pseudocode or algorithm of training, and I'll break this down like step by step. But for now, at the very beginning, when we create our neural network, we just randomly pick weights and biases. There are ways to like smartly randomly pick them that we'll cover in a future lecture, but we just randomly pick them, right? And so then we take our data set, right? And we see how good our neural network is with our random values, right? So for every data point, we do something called forward propagation. And all forward propagation is, well, it's what we've been doing this whole time of taking an input and passing it through a neural network to get our output, right? Forward propagation is just taking input and trying to get an output from the neural network. So once we get that output, right? Well, so if we put random weights and biases, it's probably going to be wrong, right? It's probably going to be very wrong. So we quantify the error of our input, of our neural network with something called a loss function. And then we use that error to pick our weights and biases, right? Okay, so let's cover forward propagation in a little bit more detail. Our outputs, again, in supervised learning, we know what our output should be in our data set, right? So that's called the ground truth. Again, it's what the true value is for our output. So that's what Y true is here. So you can see here, again, I'm just passing this inputs into my randomly chosen weights and biases. And I get minus 0.44. That's like, I didn't even get the sign right? This is like kind of bad, right? If I were doing like binary classification, like this is mapped to a 0 when it should be mapped to a 1. Very wrong. Okay. Again, a perfect neural network would output that 0.5. Okay. So I'm going to switch visualizations once again, so please bear with me. Again, I'm just going to move like this representation to this one down here, where I like graph the actual the ReLU instead of hiding it away, right? So this first neuron has an activation function of ReLU. The second neuron, our output neuron, just has an activation of like f of x equals x, right? So all I'm doing is just like I'm just visualizing this down here. Does anyone have questions about this visualization? If not, it's gonna have like a tough time going forward. So is it clear? All right, perfect. Again, this is the ReLU function, right? Mapping inputs that are negative to 0, outputs that are positive are just not changed. Okay. So again, with our random neural network, we have an output of 1.8 when the true output is 3, right? So we want to quantify how badly our neural network did. That's the goal of forward propagation or the forward pass. So our loss is some metric we choose that quantifies how bad we did, right? So no matter what the loss function or loss metric you choose, we always want the rules that a loss of 0 means the model is perfect. Like it got absolutely nothing wrong. It outputted a 3 when it was supposed to output a 3. A loss of 0.03 is like, that's pretty good, right? That's very close to 0. Whereas a loss of like 12, it's like really high, pretty bad, right? And again, what a good loss value is depends entirely on what your data set looks like and what your loss function is, right? So honestly, in some cases, maybe a loss of 12 is pretty good, right? Like, it depends totally on your data set, right? But a loss of 0 is always like the standard. We never want a negative loss. That just gets confusing. Okay. So here is a very simple loss function, right? A very simple one. We just take the true value or the ground truth and subtract it, what we outputted or our prediction. And that difference is our loss value. Why don't we want this? Well, remember, we want to keep our loss functions simple. An output of 0 means an error of 0. So negative, this would introduce a negative loss, which gets kind of confusing. What's an easy way of avoiding a negative loss?
Absolute value.
Absolute value. Perfect. So mean absolute error. That is a very common loss function. You just take the error, make an absolute value, and you're good to go. So the benefits is obviously always positive, and you penalize like all deviations linearly, right? So that's in contrast to mean squared error, right? So again, by taking the square of something, it always becomes positive, right? But the difference with this is that large values get exaggerated and small errors or small values get minimized, right? So for example, if your mean squared error, or sorry, if this y true minus y pred is like 5, for example, right? That gets like beefed up to 25. It gets increased by a factor of 5. Whereas if your difference is 0.5, well, your loss actually shrinks to 0.25, right? So we use mean squared error when, if the model's close enough, right? Like we basically say, okay, you did a good job, right? A 0.5 is like maps to a 0.25, a 0.1 maps to a 0.01, and you're basically good enough. But we really penalize large loss values, like values greater than 1. Like a 2 gets sent to a 4, 4 to a 16, so on and so forth. And again, you choose your type of loss function. There's a ton more than this, by the way, based off of whatever suits your data set, whatever suits your problem. Okay, so just some review, right? All we're doing in our forward pass is just taking an input, getting an output, and getting that loss value that tells us how bad we did. Again, right now, we're still with our random weights, we're still with our random biases. Now, back propagation is kind of the brains behind training. This is, okay, given the loss, we want to calculate how much each of these parameters, so when I say parameters, I mean the things we can change. So the weights and biases. So we want to figure out, okay, how much does each weight and bias contribute to that loss function, to that loss? And then how can we then update each weight and each weight and bias to then lower the loss, right? And so, yeah, if we can answer, okay, how much each thing contributed and how much to change it, then, well, we've basically solved how to fix our neural network. Okay, so to do this, we have to use a little bit of calculus, right? So again, our loss is value is a loss function, right? So you can imagine it as a function of our parameters, right? So in this case, we have 4 parameters, 2 weights, 2 biases, right? So our loss is a function of those 4 parameters, right? And we want to see how each weight, for example, in this case, weight 2, affects the loss in isolation. Like in this case, well, so let's say like our weight 2 and the loss has this relationship. Well, you can see if I increase the weight, my loss is going to drop, right? If I decrease the weight, well, then the loss is going to increase, right? But in practice, well, we don't have this nice function. We don't have this nice graph, right? So how do we kind of figure out what direction to move our weights or parameters in without having this nice visualization of the entire function? Can we only know the behavior at like this point, right? The slope, exactly, or the derivative, right? Yeah, so the derivative or the slope, how changing W2, yeah, the derivative is how does a change in this variable affect the output? That's all the slope or derivative is, right? So again, we can clearly see the derivative here is negative. So what that means is increasing the weight decreases the loss. So to minimize the loss, right, we take a look at our derivative and we go in the opposite direction. So if we increase W2, right, we decrease the loss, right? And so yeah, so let's say, so yeah, we started with a W2 of 0.8. Let's say we started with a W2 that's, like 1.2, like over here, right? Same idea, right? The derivative in this local area is positive. So increasing W2 increases L. So if you want to minimize loss, which direction should we go? Increase W or decrease W? Decrease, right? Exactly. So the notation we like to use is the partial derivative. So if you've taken multivariable calc, hopefully this should be reviewed for you, right? If not, this is just a fancy way of saying like the derivative with respect to this specific variable. right? Like in single variable calculus, like Calc 1 and 2, I think, we're just doing like y, the derivative of y relative to x, right? All we're doing is, okay, let's say y is a function of like 5 different things. We just want to see how like changing one variable impacts the output. Okay, so this is called a partial derivative. Okay, so again, let's say we calculate the partial derivative and we get a negative value, right? And so to decrease the loss, we take the negative of the partial derivative and move in that direction by some extent. We follow that arrow and we want to end up in this minimum, right? So again, if W2 ends up here, then we've done all we can to W2 to minimize the loss, right? Same thing if we start over there. So yeah, so okay, the derivative tells us in what direction to go, right? So could we not just subtract the derivative from the weight, and that's how we update our weights and biases every single time? Just you guys find any problems with this by any chance? Like, so take a look at what our x-axis is, 0.8, 0.6, and see how big our derivatives are. Do you guys see a possible problem with just directly subtracting our we overshoot, perfect. Yeah, so if we like subtract, or sorry, if we go to this magnitude, we're all the way over here. We're worse than what we started off, right? So how do we fix this? Well, we just go into smaller increments, right? So we add this idea, or so this the scalar value of a learning rate. So learning is just a very small number, right? And we pick this ourselves. This is not learned. Before we start training, we just say learning rate of 0.01, right? It's usually smaller than that, actually. And so what we're doing by using this very small learning rate is we're just guaranteeing that we don't overshoot and we go in very small footsteps towards that minimum that we really want to get to, right? And so with the small learning rate, we'll avoid we'll avoid overshooting, but you can imagine it'll take a lot of steps to get to that minimum. It'll take a long time to get there. With a large learning rate, okay, we can move a lot faster, but we risk overshooting, right? So oftentimes what we do is, okay, it's like we don't want to wait forever to train our model. We might start with a very large learning rate, especially let's say we're at the peak of this function. We take large steps at first, and then over time, we decrease that learning rate, right? So that way, let's say like we're down here, we have a very small learning rate. Does that make sense?
This is basically gradient descent.
Yeah. But yeah, this is gradient descent. This is a very fundamental idea of machine learning, right? Again, the gradient is just a vector of all partial derivatives, right? So again, this value, dl over dw2, that's one partial derivative. The gradient is, okay, we just collect all of our partial derivatives for every single parameter, right? So if we have like 3 weights, 2 biases, 5 parameters, our gradient will have 5 items, right? And it's called, so that's the gradient. The descent is just, well, we descend, we try to go as low as possible in each of our loss functions, or sorry, in each of these graphs. Okay, but you can imagine, okay, so if we start in this orange area and we follow the gradient, we'll end up down here. What happens if we start in this green area? Well, we'll end up in this local minimum and we'll just get stuck there, right? Because does anyone know what is the gradient right at that minimum? 0, right? So that means we just won't move anymore. So how do we avoid getting stuck in local minimums? Well, that's a problem for another time, but if you're interested, this is the idea of optimizers. If you've heard of Adam, that's a very famous optimizer. But we'll worry about this some other time. Okay. So in practice, right, how can we calculate every single gradient, right? When we're running code, we actually don't. We really want to avoid doing that. We use machine learning libraries, like if you heard of PyTorch, TensorFlow, those handle calculating the gradients for us, right? So how does it do it? Well, kind of what we need to calculate our gradients with respect to each function are these intermediary values. So 2 times 0.5, we want to save that, right? That's 1. 1 times 1 plus 1, that's 2. We want to save that as well, right? So we save all these intermediary values, right? And then that lets us calculate the gradients later on. That's how PyTorch and TensorFlow handle it. So yeah, Okay, so again, in backpropagation, the idea is to find the gradients and then take the negation of that, right? And that tells us for every single parameter, how do we update our function, right? To minimize the loss function. So again, we do one forward pass, get the loss function, right? We use the loss function to tell us how to do gradient descent, right? So, yeah, so a recap of training, right? For every single data point, we do one forward pass, one backward pass, right? We go through our entire spreadsheet, and then we keep going until we reach a loss value that we're happy with, right? And so this is the process of training, right? Picking our weights and biases to get correct predictions. A lot of times you might hear this called fitting, like fitting a neural network to a curve or function. Training, fitting, I like to call it training. Okay. So there are two common problems with training or fitting a neural network. The first is called underfitting. So this is when the model fails to learn the pattern in the data. Let's say the pattern is x squared, right? A perception can only learn a straight line. So you would say a perception underfits to that data set, right? So there are a ton of reasons why a model might underfit, but the most common is when it's not complex enough, right? Again, a perceptron or a neural network with not enough neurons, right? So again, we call these oversimplified models, or we say that these oversimplified models have a high bias. They're too simple to fit to the data set. You could also say that if you just didn't do your forward and back propagations enough, right? Because the idea of training, okay, we do one forward pass, one backward pass. That's one set. And then we do it again. And then we do it for as many times as we want. If we stop that process prematurely, then we haven't reached that local minimum. And then, you know, we just haven't trained for long enough. This is a little bit more of a tricky situation, but this is when we actually have like important features that are missing, right? Let's say we want to predict like what I'm going to eat tomorrow, right? Or what I'm going to eat in a couple hours. Well, it would probably be useful to see what I've eaten thus far, right? If we leave that data, predicting that function is going to be very hard. On the other hand, if we have a bunch of useless features, we might fit to a bunch of gibberish and then have that problem. So if you are missing features, you might underfit. If you have too many useless features, you might underfit as well. Okay. Yeah, so again, this is our three neural network, right? It was able to fit to a quadratic function, but the moment we have this cosine shape, no matter how we tweak those weights and biases, we can never fit to this data, no matter what we do, right? That's underfitting. Overfitting is the exact opposite problem, right? It's when the model learns all of the underlying patterns, including the noise of a data set, which makes it difficult, it fits to outliers, which makes it difficult to learn the general pattern, right? So when you have a bunch of neurons, so the other way around, right? You have too many neurons, right? Your model gets more expressive, which means it could fit to more and more complex functions, right? So again, so we finally have a rigorous definition of variance, right? So variance is when you commonly have a very complicated or very deep model with a bunch of neurons, right? And a single input can cause your model to change a lot, right? For example, when you're doing back propagation, right? A single outlier can cause your weights and biases to skew towards that outlier, right? Making predicting normal data points a lot harder. Again, if you train for too long, right? You again risk learning all that noise, all that garbage in your neural network. And if you just don't have enough data, you might learn the patterns in that very small local data sets instead of those larger global patterns. So here's kind of an illustration showing what I mean, right? So what we want is this general pattern that we pick up on, right? So if we add more yellow and red dots, they'll kind of follow this breakdown, right? Overfitting is when we when we correctly classify every single thing, but then we have this very strange function, right? You can think of these three yellow dots as outliers, right? If I add 100 more yellow dots, this neural network would probably get them wrong, right? Yeah, I've overfitting twice. No, okay. Underfitting is Okay, I have it in a different example. Yeah. You can imagine underfitting is like if we fail to learn a curve and we just have like a straight line or something, right? Okay. But you could kind of see like a little bit of contradiction here, right? Like the whole point of training is to minimize our loss, right? To fit to our data, right? So like if our loss function is very low, right? That tells us we do good and like that effectively tells us we did a good job. How do we know if our model is overfitting? Or like how do we know when to end training as opposed to our loss just going really down? Exactly, yeah. So what she's talking about is splitting our data into a training set and a testing set, right? So with our training set, right, this is the data that we're doing backpropagation on, right? That we're training on, right? So this is how we pick our weights and biases, right? Now, the testing set is never used in training, right? So like the models has not been changed by the testing set. And so once we finish training, we can then test our model on the testing set and see how well it did, right? Because you can imagine that the model will always do really well in the training data if it overfit, but it would do bad on the testing data, right? Because it hasn't learned that general pattern. Conversely, if you underfit, I guess you just do bad in both, right? You just do bad. So we have this testing set separated from our training set, so we can like have an unbiased metric of how well our model is doing. Again, the more data, the smarter our model is, though, right? So we want to have as much data in our training set as possible, but we still want to have enough so that our test set is representative of the entire data set, right? Like if we have like 5 things in our test set, right, out of like a million data set, those 5 samples are not going to represent how well your model did, right? So generally like 80%, 20%, that's usually a very reasonable split. Okay, so we have a few different beyond our loss function, because again, the loss function could vary a lot based off of your problem, right? We have a few more standard go-to metrics, right? So the first is accuracy, right? Again, just the number of total corrections divided by the total predictions. This is kind of your go-to, right? Your bread and butter. Recall is the number of true positives over the number of true positives plus false negatives. Precision is true positives over true positives plus false negatives, right? If we kind of want a holistic output beyond just accuracy, we can have this area under the curve model where the y-axis is the true positives, the x-axis is the false negatives, right? So if our model follows exact green line, then it's done perfect, right? It's done all the true positives correctly. It has no false negatives, right? Generally, our model would follow more of this curved shape. A worst case is that like, we have like zeros on both. Okay, but again, in most cases, we usually just use accuracy, right? It just, when you're like being very rigorous, like in papers, for example, you'll see recall precision in some area under the curve stuff. Okay, sorry. Do you want to?
Oh, yeah.
Yeah, you got it. Okay. So I think I've done a couple reviews of training. Does anyone have any questions about training, test sets, train sets, evaluation? You good? Does anyone know why like we would bother to have separate like metrics like accuracy instead of just using our loss function to grade like how well our model did?
Model for for example, hospital, you want to like specify I want to be more certain kinds of decisions. So it's using sometimes I want more accuracy, sometimes I want more precision. Yeah, it's like that.
Yeah, like for like a hospital, let's say like I'm predicting if a patient is sick or not, right? If I come to you and say, hey, my model did really well and I had loss of 2, do you know what that means? Right? Like you'd ask, okay, what's your loss function? Right? What does your data set look like? Now, if I say, hey, it accurately predicts if a patient's sick or not with 99%, well, that's very clear, right? Okay. So yeah. Okay. So I know we've gone a little bit over time. That's my bad for showing up late. Now, if you guys have to go somewhere, now would be a good breaking point. I do have like the next few slides will be an example of forward propagation, back propagation. I kind of hand waved away those examples. But now at this point, you have a pretty strong conceptual understanding. So if you want to see the rest of this lecture, need to go now, please scan that QR code. That just takes you to our website. But if you guys have a bit more time, I'm just going to go through an example of forward backpropagation. All right, raise your hand if you're staying. All right, appreciate you guys. Okay, so let's do an example of a single pass of training, right? So one forward propagation and one back propagation. Okay, so again, forward pass, send in inputs through our neural network, and then get that loss value, how badly we did. So just for convention, right? The output of a neuron, so that's where we are with that yellow, with that cyan circle. We denote the output of a neuron as Z1. Sorry, we output the output of a neuron before the activation function as Z1. The input is X, the weight is W, the bias is B, right? So anyone good at mental math? 2 times 0.5 plus 1. That is 2. All right. If we pass 2 through the ReLU function, what do we get as output? 2. Nice job, guys. All right, let's keep going. 2. Oh, I have the answers right. Okay. Well, okay. Yeah. So yeah, here I just have these intermediate values. These will be key in backpropagation, right? So you know, we have the output pre-ReLU, right? We put that input through the ReLU function, and then our final prediction ypred is this 2, right, which we are calling A1, times the weight plus the bias, right? So how many neurons do we have in this example, if anyone knows? Close. 2, right? I could see why I said 3, maybe like the cyan circle or cube, but we have one neuron that spans from this, okay, that has this one weight of one bias and a ReLU activation. Our second neuron is our output neuron, where we have one weight, one bias, right? Because we only have one input, so one weight. And we really have no activation, right? So we just kind of skip that step. So 2 neurons. Okay, so our loss in this case is our mean squared error loss, right? Remember how I said like our loss functions are kind of like hand wavy, right? As long as it's close to 0, we're doing kind of good, right? So that actually gives us some flexibility with like modifying it. So this is mean squared error, but like I put a 1/2 here, right? Remember how like with backpropagation we're doing derivatives, right? This 1/2 simplifies the derivative a little bit, but we'll get into that later. For now, just bear with this 1/2. So our loss, 1.8 minus 3, right? We square that value, take half, and that's 0.72. That's the entirety of our forward pass for one data input. You can imagine if we have more data inputs, right? We do this process for every single one, right? Okay. Yeah. So now that we have like for the single input, how do we do backpropagation? How do we fix our neural network, make it better? Okay. So with backpropagation, we kind of start from the end and work our way to the very beginning. So we start by finding the gradients of W2 in bias 1, right? So we start with the parameters of our output neuron and work our way back. So I'm going to start with W2. You could start with B2. It doesn't matter. Okay, so how do we do that? Again, we want that partial derivative, right, with respect to the W2 weight. Well, so it's a little bit of calculus review. This is why I kind of save those intermediary values, right? So yeah, so we have W2. We want to track how W2 changes our final output. So, we treat A1, so the output of our ReLU, as just some like, coefficient to our input variable. Same with that bias. And then to get the derivative, we take the chain rule. Do you guys remember what the chain rule is? So to take this derivative, we have to take the derivative of the loss with respect to the prediction itself times the derivative of the prediction with respect to the weight, right? So what happens, like how long do you think I'm just not gonna ask a question. You can imagine that for this weight 1, our chain is gonna be a lot longer, right? Our chain of derivatives. Does that make sense why? Okay, I'm not gonna prove the chain rule right now. If you guys have any questions about that, definitely feel free to stick after or like ask me, right? But this is how you take a derivative when you have kind of two layers of functions in between, right? Okay, great. So, we take that derivative, right? So what's the derivative of y pred with respect to W2? It's A1, right? So that's equal to 2 in this case. What's the derivative of L with respect to y pred? That's just y pred minus y true, right? So that's kind of why I had that 1/2 from earlier. Okay, I'm missing it up here. But that's why I had that 1/2 from earlier. Like the derivative of like y paired minus y true would be what is it? 2 times this value. By having that 1/2, we kind of just hide away that coefficient, right? Okay. So this value on the left is 2, this value on the right is minus 1.2. We multiply them together to get minus 2.4. Okay, so that is our gradients for W2. That is our derivative of W2. Sorry, the partial derivative of W2. Okay, cool. So we now want to update W2 to make it better, minimize the loss. So we take the negative of that partial derivative, that's why we have a minus sign here, and we scale it down, right, using our learning rate of, in this case, 0.01. And again, we don't learn a learning rate, we just pick one from the get-go, right? Throughout all of training, our learning rate will be 0.01. Now, there are some advanced methods that do have you learning a learning rate, but in this case, we're not going to worry about that, right? Okay. Yeah. I was going to ask why not have a 1 as your like why bother with the learning rate, but you guys know this. Why do we need a learning rate? So we don't overshoot. You guys are paying attention. I appreciate it. Okay. As I said earlier, right? Let's say we wanted to calculate the derivative of something farther back, right? Of W1, for example, right? Well, we have exact same process, just the chain rule has our chain of derivatives a lot longer, right? So again, that's why we need these intermediary outputs of Z1, A1, Y pred, L, right? So, do you guys want me to go through these derivatives, or is it kind of clear as what we're doing here? All right, I appreciate it, right? Again, we're for each stage, right? We're taking the derivative of that stage's output with respect to that stage's inputs, right? So when I say stage, I mean, okay, for this section, the derivative of loss with respect to the y pred, and then the respect of y pred with respect to A1, A1 with respect to Z1, Z1 with respect to W1. So we have that chain of with respect to's.
So when we're doing, do we use our updated values? Like we updated A1 for example. Do
Good
we
question.
Use those in units?
Yeah. We don't update our weights or parameters like in between doing backpropagation. We calculate all of our gradients with the old values, and then we update everything at once. Right? That's a very good question. Yeah, so like we didn't change our W2 of or maybe I did. I hope I didn't. Yeah, we didn't change our W2, like it's still 0.8, right? We calculate our entire gradient, so the derivative of all of our parameters, and then we update all of them together. Okay. Yeah. Yeah, so a very common practice is like a common homework is like, make a very simple neural network with like 3-4 neurons in Python, right? So all this would have you do is like, okay, like just for each derivative, you just like write out the function yourself, like which we did, right? Like we just turn these into Python functions, for example. And then same with our derivatives, right? Like, the derivative of y pred W2, that would be another function that just equals A1. So if you guys have some time, I know it's the re-class, so this is not homework or anything, but it's always a good kind of learning experience to try to build this on your own in Python. Next lecture, we'll be covering like actual coding and stuff with PyTorch. That hides that like all these intermediary values, you do not have to worry about any of them. PyTorch or TensorFlow, the alternative, those hide those away for you, handle everything. All right. I appreciate you guys sticking with me this long. Next lecture will be starting at 6. Sorry about that, guys. And I'll try to keep it to under an hour, ideally 45 minutes. Oh, one last announcement. I will be making this to Discord, but we are having our first competition by Seth, one of our officers, on September 28th, right? So we're gonna try to get some pizza for like, I don't know, like 6, 7 boxes maybe. I didn't do that intentionally. I'm gonna have like a small crash prize of $20, Amazon gift cards. But if you guys have ever used Kaggle, it's like a common platform for doing ML competitions. So yeah, instead of a GenBot meeting, on the September 28th, we'll be doing the competition instead. And yeah, I think it'll be a lot of fun. I don't want to give you guys homework, so this will be a good way of just practicing some of these skills that we're learning in lecture and getting some money if you win. All right. Okay. Next time we're going to be doing a bit of coding, a little bit more on training. Otherwise, if you have any questions, stick around. Thanks for coming, guys. See you next week.